speaker, who will be our first speaker, Professor Bart Ketelaere. I always mispronounce his last name. Bart's a great guy. He won the Young Statistician of the Year award for INVIS a few years ago, and his career has been blossoming ever since. He does wonderful work dealing with imaging and its applications within quality. So, Bart, I'll turn it over to you. I'm looking forward to your talk.
Thank you for inviting me for giving a talk here. It's greatly appreciated. I'm glad to be part of the ISEA Online Summit. So my talk, in fact, will be about a statistical engineering case study related to industrial sorting. And in fact, it's, let me see whether I can, yes. So in fact, it's a joint effort between different research groups in academia. So it's a mechatronics, biostatistics, and sensors research group I'm affiliated to. It's also the research group on robust statistics who is involved, and also an important company that builds sorting machines for, let's say, a quite broad range of products. And the talk will be, in fact, about optimizing those product sorting machines. So that's what it's all about today. So what I will first do, I will first give a short description of the application, give some context about it. And when you look here, this is typically a sorting machine you see. And well, in this case for nuts, the goal is in fact to sort the nuts according to their quality. So it can be good quality, it can be bad quality. But not only that, sometimes there are also unknown objects in the material stream. So let's say parts of glass or wood or stones that are also within the process stream. So those need to be detected as well. So typically what's done, it's a computer vision system that is looking at the material stream. So a long time ago, it were persons looking at the stream and sorting out all the product manually. But nowadays, this is done by using machine vision. And such a machine vision, in fact, consists of two major components. The first one is the camera system itself. And this camera system itself generates the data. And those data are typically, well, for each pixel in an image, you have typically three-dimensional information, being the intensities of the red, green, and blue. And modern vision systems even go beyond that and also look in the infrared parts of the spectrum to gain more information about that. So that's what we call hyperspectral imaging. So in fact, you have the imager, it produces the images, each pixel has the values, and those are the inputs you want to use for making a classification algorithm. But when we talk about a classification algorithm, it means that we have somewhere to train the system. And if you want to train the system, well, we need trained or labeled data, sorry. So an important part of getting the data is also to have the right labels. And when we talk about getting labels, in practice, there are in fact two main approaches to it. The first approach is what you see here. So actually what's done is people manually sort the different fractions, for instance, the different grades of the nuts. Once you have separated those in the different classes, you just take images of the pure product classes. And because you know it's kind of a pure product, you automatically label all the pixels in those images to the class it belongs to. So that's one of the classical ways of doing this. But sometimes also impurities might be present, as I told before. So this could cause some issues with the labeling. So in fact, what you're doing there is you attach the wrong labels to some of the pixels. Besides this first approach, you also have a second approach to it. The second approach to it is in fact to not manually label, or sorry, to not manually sort the products as such, but to acquire images from the products as is. So you present to the camera system your material stream with the different classes being present. And then what people do is on screen start manually labeling those pixels. So that's what you see here as well on this image. So it's an image about grain kernels. And in blue, you see some of the pixels that are labeled, let's say, for class A grains, and the red here are for class B kernels. So it's also manual operation, and it's done completely on screen. So let's say those two approaches are what people classically do in this industry. Of course, both have disadvantages, and they're kind of common, let's say, because the first one is that, well, both are quite time consuming. Sorting out the product costs time, but also to just pinpoint the different pixels on screen is also an operation that costs quite some time. So it's time intensive, and we cannot avoid it, of course. Every time we have a new product we want to inspect, we need to redo the whole labeling procedure. So it's time consuming, and there are some challenges related to it as well. And the main challenges are listed here on the slides. And the first challenge is, in fact, the fact that often you have bad sensor readings. And if you have bad sensor readings, those bad sensor readings, they can, well, compromise the quality of your data. And the bad sensor readings mostly come due to the fact, for instance, that there is dust or dirt in between the camera system and the product you want to inspect. There is electronics noise and so on. So it's inevitable that you have some noise on your image data. And this type of noise on the image is what we will call the measurement noise. Besides the noise on the measurements themselves, you also have this mislabeling I talked about. So in this manual labeling process, the operator can mislabel a product from class A to B, or if there are unknown objects which are present in the image, those can be classified, let's say, as a wrong product. And those mislabelings is what we will call during the presentation the label noise. So those two words, or two phrases, the measurement noise and the label noise, are two things that will come back in the presentation quite a lot. So that are the main challenges here. So we have a lot of noise in the data, and still what we want to do is we want to build a classification algorithm for the sorting machine, which is, let's say, robust to all different sorts of noise. So the problem that we have here, and that asks for a statistical engineering solution, is that in fact the company realizes that quite often the data is contaminated, and they don't want this contamination to be destructive, let's say, for the classifier that is being built. So that's important. The company also sells to a lot of customers, so it should work for all customers, the solution that we have in mind. And in fact, the company has quite hard times in building those classifiers. So the classification is central to a sorting machine, and the company realizes that it has some hard times when there is quite some noise present. So it's a problem which is kind of company-wide. So for the different departments, the different clients they each time have the same type of challenges. So, okay, so if we then look at those challenges, and let's now look at the goals and the stakeholders that are connected to the project. So when we had the meetings with the different stakeholders, I will say something about it later on, we identified three main goals. And the first goal was that, well, we should be robust against the measurement noise. So there is a trend towards measuring faster and faster. Sensors become cheaper and cheaper, and all those trends, in fact, increase the probability of having measurement noise present in the data. The second most important goal is that we should also be robust against this label noise, because people realize that a manual labeling step is inevitable when doing the reference measurement for the classifier. And the third one, which is important when you look at real-time classification, is that whatever the solution at hand, it should be a very fast solution or a very fast classifier. So those modern sorting machines, they really operate at very high speeds. There are many thousands of pixels that need to be classified in a fraction of a second. So being fast is really crucial in a solution here. I thought that we had meetings with different stakeholders, and in fact, what are the stakeholders here in this project? Of course, there is the company. So the company owns the problem, let's say. So they have the sorting machines and are looking for a solution to it. And they realized that if they want to have a solution which is broadly applicable, there is a certain need for novel approaches that stretch beyond their sole competence. So that's why they knocked on the door, let's say, of our labs. And what we did is we set up a kind of a triple helix story. That's how we call it. So there is a strong teamwork and collaboration between different players. And those players are the people from industry, as I said, that own the problem or the machines, let's say. We have us from academia that are providing some potential solutions. And also important is that government is involved in this. And they're in fact involved by providing budgets for supporting innovative companies here in Flanders, part of Belgium. So when they do that, in this case, for instance, through awarding industrial doctorates, those are PhDs or PhD students that actually work at the company, but that collaborate very strongly with academia to make a PhD on a very specific topic. So that's what we, in fact, initiated with the company. What's very important in this project, but I think in every statistical engineering project you want to do, is that there is a very strong motivation by all the stakeholders to start this case study, because we have to realize that a solution for this problem is not something you do in a framework of 6 months or even 12 months, but it's a kind of a project for several years. So everyone here was motivated in starting this trajectory, realizing that it's something that will take up quite some time. So that's, let's say, a bit of a background here about the case study we are dealing with. Okay, so when we then had the meetings with the stakeholders, we kind of defined a certain strategy on how to attack the problem. And in fact, there were 4 different aspects that came to mind. The first one is what I mentioned already, is that, well, we should have robust versions of the classifiers which are now used at the company. And what I will show in this work is mainly based on quadratic discriminant analysis. So that was kind of the first work that needed to be done. So we need robust versions of it. But when we design those robust versions, which of course should be very fast, as I mentioned, we should very well investigate how robust they are, both for the label noise as well as for the measurement noise that are present in the data the company typically gathers. Now, an important part as well is when we are sorting, as I explained, for instance, for the nuts, you have the good and the bad quality, for instance. But besides those known quality grades, you often have some unknown objects that are present in the data set. For instance, the pieces of glass, wood, and so on. So those are unknown in advance. And the company also wanted to have an idea on how many of those unknown objects are in the data or in the material stream. So we need to do something to allow for a class of unknown objects besides the objects we want to classify in the predefined classes. I will show this is something we will do through the use of tolerance ellipses. And then the fourth and last, but I will not handle that in the presentation probably here because it will take too much time. But another important part is that they want to have a kind of a graphical display that provides insight in how bad it is related to the measurement and the label noise. Because if the company would have information on how much label noise there probably is or measurement noise, they can start kind of an improvement trajectory to decrease that. So we worked on a graphical display of that as well that tries to separate between label and measurement noise. But as I say, I will not handle it in detail here, but just to mention that it's an important part in practice as well, that you gain insight in the structure and the eventual problems of the data you have. So starting point is the classifier which was used, which is a classical quadratic discriminant analysis. And I will not go in detail through the slide, but I think most people know what it is doing. So actually you assume that you sampled p-variate observations from the different classes, and you assume that for each of those classes, the observations follow a Gaussian density function with a certain location mu and a scatter matrix epsilon. So That's what you assume, let's say, as the basis for the discriminant analysis. Now, in the classical version of discriminant analysis, you estimate the location and the scatter just by the mean vector and the sample covariance matrix S. So that's what you typically do. And once you have estimated those, you can calculate here the discriminant score here, and you assign a certain observation to the class for which this discriminant score is maximized. So that's the classical approach to discriminating or of a quadratic discriminant analysis. So that was kind of the starting point for the classification, for which the company realized that it was quite sensitive to the measurements and the label noise. So just to show or to illustrate the fact that the classical quadratic discriminant analysis is quite susceptible to label and measurement noise, what I did here just for visualization is you have here two classes, and what you see here by the black line or the black curve here, this black curve is in fact the decision boundary, which is based on the quadratic discriminant. So this is the clean data set. Now, if we add some measurement noise to it, and that's what you see, sorry, some label noise to it, and that's what you see here, you see several of those blue points which are inside the orange data cloud, and vice versa. Also, you have the orange points within the blue data class, so that's a clear mislabeling that took place here. Well, you see that the decision boundary of the classical discriminant analysis is shifting quite a bit. So it's sensitive to providing the wrong labels, and the same in fact holds for the presence of outliers. So you see some outliers here, especially in the orange class, and you can see already how those outliers influence the exact location of the decision boundaries of the quadratic discriminant analysis. So that's typically something we don't want to have. And even worse, if we have a combination of the wrong labels and outliers in the measurements themselves, you see that the decision boundary even is influenced much more. So that's the actual problem the company was constantly fighting to, like, okay, if I have those mislabelings and outliers in my data set, I see that my classification algorithm is performing quite poor and is not stable. We want to get rid of that issue. Okay, so as I said, as a first goal, what we wanted to do is to have a robust version of this quadratic discriminant analysis. And having a robust version of it, well, you start with using robust statistics. So it's widely known, I think. So what it does, it's a class of methods that emulate popular statistical methods, but methods which are not unduly affected by outliers present in the data set. It's quite an active field of research. I think it holds great promise and great opportunities in industry, but at the moment, I still see that it's kind of underused. And probably one of the main reasons it's underused in modern industry is that it comes with quite a lot of computational burden, as I will show later. So it's robust, but it takes a lot of time to calculate the robust versions of the classical parameters you want to have. So that's something that needs to be resolved. So I will now shift to a very short description of the path we followed in designing, let's say, a robust version of discriminant analysis. So I will not provide any statistical details, but it's more the process I want to show you in this whole exercise that we made. So if you look at the robust version of quadratic discriminant analysis, it's in fact exactly the same as in classical discriminant analysis. The only thing that changes is that for the location and the scatter, you just plug in robust versions instead of the classical versions. So when you plug those in the classical discriminant rule, you have a robust version of quadratic discriminant analysis. So far, so good. That's an easy thing to do. But the question, of course, will be like, okay, what will be the estimators for mu and for sigma? So that's important. So we need a good estimator there that's fast enough to be computed in a kind of online setting. And The path that we followed here, well, actually the work on robust estimators, especially for the variance covariance matrix, it's a path that's already taken a very long time ago. I think that one of the most used principles is using the minimum covariance determinant, so MCD, is how it's abbreviated. So it's a method which was developed already in '85 by Rousseau, one of the co-authors here, and it provides a very robust estimate for the covariance matrix. So that's a very good thing, but as I mentioned before, the problem is that it's very computational demanding to calculate. And nowadays, data sets become larger and larger, dimensionality is increasing, so it's prohibitive to apply in a real life setting, let's say. And that motivated several researchers. 1999, the same author, Rousseau, made a kind of a first version of it. And this fast version was even improved later in 2012 to a method which is called deterministic MCD, which was much faster even than the fast MCD, which was very robust, but still, if we make calculations, it's still prohibitive when you want to use it in a real life setting. And that was the kind of a starting point of the statistical engineering project we started about 2 years ago. The first thing we did is we designed what we call a real-time DetMCD method. So as the name suggests, it's based on the DetMCD principle, but it's a real-time version in the sense that it's, well, several orders of magnitudes faster than the DetMCD. So also here, I will not provide the details, but it was a very nice, well, let's say sub-project of the larger project I'm describing now, because this real-time version not only includes advanced statistical methods, but it's also strongly related to computer architecture, computer science, and so on. So there are different disciplines that need to come together to provide this kind of intermediate solution to the whole problem. But I think that's the typical thing that you do or see in statistical engineering. It's something that stretches beyond what one or two parties can do, let's say. So it's much broader than that. You need people from very, very different disciplines to come up with the total solution. So when you have this real-time version and you plug it in the quadratic discriminant analysis, you have the method which we call real-time robust quadratic discriminant analysis, full stop. So that's the method, in fact, that will replace the classical discriminant analysis in this sorting machine. So it's fast. We know that it's robust under, let's say, several simulation frameworks. But of course, we also want to check it here against the label and the measurement noise in practice. So that's something we needed to do to be able to answer the second need or the second goal, namely to check it for the robustness against those two sources. So that's actually what we did. And that's an important part, but before just giving the details on how robust it actually is, I just come back to the fact that I said, like, one of the goals also was not only to classify the different classes, let's say, of the nuts, but also you want to allow for kind of anomaly detection so that you have a clear view on the amount of unknown samples in your data set, the pieces of glass or metal or wood or stones and so on. So that's, especially in the food industry, it's a very, very important part, because you often have a lot of samples which you don't know what it exactly is. So you want to have an idea on what happens there. And the fact that it's important, well, actually, if you look at most classical classifiers, they have in fact a disadvantage that every sample is assigned to one of the known classes. And this is exactly what we don't want to have when we are sorting those food products. So what we did in order to solve it is that we say, okay, what we can do is for each of the classes we have in our quadratic discriminant analysis, we can calculate the tolerance ellipses. And if we calculate the tolerance ellipses and we see, and we look for each new sample, whether it's falling within the tolerance ellipses or not, well, we can make a decision on whether the new sample belongs to one of the classes we have seen before, or whether it's something we have never seen. So that's a kind of the extra rule that we added to this real-time robust discriminant analysis, that we say, okay, if now our distance of our new point to all the classes is larger than a threshold value, we just assign the new observation to a class of unknowns, or a zero class, let's say. So that in practice, people that are operating the machine have a clear idea on how many unknown objects are present in the data. So that's added, let's say, to the robust version, so that in the end we come up with a solution that answers most of the issues we had. So this is again the previous plot, but now for the robust versions. You have the clean data set, you have the decision boundary, you have the adding of label noise, you have also here the adding of the measurement noise. And in both cases, you see that the decision boundary is almost not influenced by the addition of both sources of noise, even if they come together. So I will not provide more examples and details about this, but this is just a visualization to say that, okay, if you build in those robust versions in QDA, you seem to be quite robust against the two sources of variation that we typically encounter in practice. I will come back to it a bit later as well. So that's important to know. So the problem of measurement and label noise is something we can handle with this robust version of QDA. So let's now go back to the sorting of agricultural produce. So this is just a very short example I give. What you see here are different cantaloupes, and cantaloupes here, for labeling, the second approach I mentioned before was followed. So a mixture of the material fractions was presented to the camera, and a human operator labeled the data into the different classes. We had 4 quality grades of the cantaloupes, about 2,800 individual pieces. And also we realized that there might be some foreign objects like wood and stones being present. So, and the question is now, okay, if we have this sorting task to perform, how is our real-time and robust classification doing for this case study? I will now show a small part of the data. So what you see here, in fact, are the 4 different classes of the cantaloupes. And I present them here, so it's more than 3-dimensional. So what I did here is present them in the first 3 principal component dimensions. So what you already see is for some of the classes, such as the yellow class, the E class here, it behaves quite okay, but it's maybe not so clearly visible. But for the blue class here, it's much more, well, less clear. Let's say you have points here and you have points here. You can also see that here. So there's a part of the data being here and there's a part of the data here. And you might see the same thing even for the H class, so the red class here. So something might have happened there when let's say, gathering the data. So it's something we should be well aware of. Just to show on this data set the importance of a robust version versus, a classical version of QDA, well, you see here the tolerance ellipse for the blue class in the classical setting, and you see the same thing here for the robust setting. Actually, behind the yellow points here, the majority of the blue points are located as well. And that's why the tolerance ellipse is located exactly here. So when gathering the data here in a sorting machine and looking at the test set, so we gathered the test set then and looked how well the classifiers are doing. Well, in the classical classifier, the sorting is based on, you see that it has in total a misclassification rate of 22%. And the 22% is not so much related to class D, which seems to be quite okay in this confusion matrix. But when you look, for instance, at classes H and HA here, those are completely ruined by the fact that in our training set, there was quite some label and measurement noise being present. But if you look then at the proposal we had here as a solution, this robust version of it, you see that it's much better for all the classes. And so the D remains very good. We have much increase in the H and in the H class, and for those two classes, we are even perfect. The fact that it's not perfect here was also visible in the data set before. There is quite some overlap in those two classes, so they are very close to each other, so it was not possible to completely separate. But the most important thing here is that the practical situation the company is encountering in practice, being the fact that the classifier is breaking down in the presence of label and measurement noise, is completely avoided by the real-time solution in a robust way that we provided here. So that was, let's say, a very good conclusion of the work we did so far with the company. So I think my time is running out, so I will come to some of the conclusions. So as I said, label and measurement noise are inherent to industrial sorting and computer vision, and it really compromises the use of classical statistical approaches. So as a general statistical engineering framework, we have set up, let's say, work with different stakeholders that includes academia and industry to design a solution to it. And we actually have shown in industrial experiments that the robustness of the methods which we propose is quite well under real-life conditions. And again, so it's only a presentation of about 25 minutes. It's only a part which I present here, but in fact, it's a much larger story, let's say, of a statistical engineering case that eventually could transform the way this industry is sorting right now. And I think this concludes my presentation. So there are just two references I list here. And if there are any questions about the presentation, I will be glad to answer them. Thank you for listening.
Thank you, Bart. That was a great talk. We've got time for a question or two. Sherry, have you been tracking questions?
Yeah, there are none posted.
Well, if people have questions, if we have time at the end, perhaps we could have that, be able to address them then. So if you have a question for Bart, send it to Sherry, and we have time at the end, then maybe he can address it. But Bart, that was great. I really do appreciate it. Thank you.
Thank you.